On June 30th, 2026, one small patch on the surface of the Sun fired off a powerful X1.1 flare. Then, over the next 24 hours, that same patch fired 10 more. One space weather scientist watching it happen live gave it a name that stuck: the Machine Gun Sun. 4 days later, on July 4th, the storm that patch had triggered hit Earth 2 full levels stronger than official forecasters had predicted. Northern lights showed up in New Mexico, in Northern California, in places that hadn't seen aurora in years. Nobody got hurt, nothing broke. And that's exactly why this isn't the story you'd expect. This isn't a story about the Sun getting more dangerous. It's actually calming down right now, coming off its peak. This is a story about something else getting more fragile while the Sun quiets down. And that part isn't slowing down at all. Here's what I want you to walk away with by the end of this video. The forecast that missed by 2 levels wasn't a fluke. It's the best our current system can do, and our current system has a built-in blind spot that's about 15 to 60 minutes wide. Today, as I'm recording this, the Sun is actually quiet. Background flares only, nothing major. But that quiet is exactly why scientists are watching more closely right now, not less. Quick question for you. Have you ever seen the northern lights somewhere you weren't supposed to be able to see them? Drop it in the comments. I want to know where you were. And if this kind of breakdown is useful to you, subscribing helps more than you'd think. Alright, let's start with what actually happened this year, because the timeline alone tells you something important. 2026 has not been a quiet year for the Sun, even in its declining phase. On February 1st and 2nd, a rapidly expanding sunspot called Active Region 4366 fired at least 4 X-class flares in about 24 hours, including an X8.3, the strongest flare of the year at that point. It triggered strong radio blackouts across the South Pacific, the kind that briefly knock out high-frequency radio communication for ships and aircraft using that part of the spectrum. Pilots flying long-haul polar and trans-Pacific routes during a blackout like that typically have to switch to satellite communication or reroute around the affected region entirely, the same basic mitigation airlines have used for years. It works, but it isn't free, and it isn't instant. On April 24th, Active Region 4419 fired an X2.4, and then just hours later, an X2.5. 2 X-class events from the same patch of Sun in a single day, each one throwing off a coronal mass ejection that forecasters had to track separately. And then came June 30th. Active Region 4479 released that X1.1, and the 10 M-class flares that followed it in the next 24 hours were frequent enough, and fast enough, that Dr. Tamitha Skov, a space weather physicist who tracks this for a living, called it the Machine Gun Sun live, in real time, watching the data come in. Here's a detail worth pausing on, because it explains why scientists take this classification system seriously. The scale that ranks flares, A, B, C, M, X, isn't linear. Each letter represents roughly 10 times more X-ray energy than the one before it. So an X-class flare isn't just a bit stronger than an M-class one, it's carrying an order of magnitude more raw energy, and within the X category itself, the numbers keep climbing the same way. An X8 releases roughly 8 times the energy of an X1. That June 30th flare, the one that kicked off the Machine Gun Sun sequence, released radiation that reached Earth in about 8 minutes, at the speed of light, triggering brief high-frequency radio blackouts across the sunlit side of North America the moment it arrived. Here's where it gets genuinely interesting, and it's the part most coverage skipped past. Several of those eruptions launched coronal mass ejections, CMEs, which are massive clouds of charged solar material, toward Earth. NOAA's Space Weather Prediction Center issued a G2 moderate-level geomagnetic storm watch for July 3rd and 4th. A G2 is not a big deal. It's the kind of thing that might nudge the aurora a little further south than usual, maybe into the northern U.S. border states on a good night. What actually happened on July 4th was a G3 storm, 2 full levels stronger than what was forecast. Aurora was visible across more than 30 U.S. states, as far south as New Mexico and Northern California. I'm not going to tell you that was some kind of near catastrophe, because it wasn't. No confirmed infrastructure failures were reported. The storm peaked mostly on the night side of North America, which is about the best timing you could ask for. But sit with the actual size of that miss for a second. Forecasters said G1, reality delivered G3. That's not a rounding error. That's the difference between maybe check your compass and commercial airlines start rerouting polar flights. So why did the forecast miss so badly? This is where the story stops being about the sun and starts being about us. The only place on Earth, or rather off Earth, where you can actually measure the exact orientation of an incoming CME's magnetic field is a single point in space called the L1 Lagrange point, about 1,000,000 miles toward the sun. It's the one spot where the sun's gravity and Earth's gravity balance out, so a satellite can sit there and just watch the solar wind flow past on its way to us. For years, that job belonged to a spacecraft called D-Scover. In mid-2026, D-Scover was replaced by a new satellite, Solar 1, built specifically to keep that watch going. Here's the catch, and it's not a flaw in Solar 1 specifically, it's a flaw in the physics of where that satellite has to sit. Solar wind measured at L1 gives forecasters a lead time of roughly 15 to 30 minutes on the magnetic field's actual orientation, the single detail that matters most. And a CME's magnetic orientation, whether it lines up to cancel out Earth's magnetic field or reinforce it, is the biggest factor in how hard it actually hits. Two CMEs can be traveling at the same speed, carrying similar amounts of material, and produce wildly different results on the ground, purely because one arrived with its magnetic field pointed the wrong way relative to Earth's own field. You cannot know that orientation with real confidence until the cloud is almost here, sliding past that one measurement point. That's the actual reason the July 4th forecast missed. Not incompetence, not a broken instrument. A fundamental 15 to 30-minute blind spot that no amount of better technology has fully closed yet, because the laws of physics put our only good vantage point uncomfortably close to the finish line. Lloyd's of London, in a widely cited 2013 risk assessment written with atmospheric scientists, flagged this exact gap as one of the core reasons grid operators can prepare for a storm's general timing days in advance, but can't know its true severity until it's essentially already arriving. It helps here to be precise about two things people usually lump together as a solar storm, because they behave completely differently, and that difference is exactly why forecasting is so hard. A solar flare is a burst of X-ray and ultraviolet radiation. It travels at the speed of light, so it reaches Earth in about 8 minutes, and by the time you know it happened, its radiation has already arrived and mostly finished interacting with the atmosphere. There's no meaningful warning window for a flare itself. It simply happens, and its effects on radio communication show up almost instantly. A coronal mass ejection is a completely different animal. It's an actual physical cloud of magnetized plasma, billions of tons of solar material, thrown outward from the sun's corona. That cloud is slow by comparison, taking anywhere from about 15 hours in an extreme case to several days to physically cross the 93 million miles between the sun and Earth. Flares and CMEs often happen together from the same eruption, but not always. A spectacular flare can fire with no CME at all, and a fairly modest flare can still be accompanied by a CME that does most of the real damage once it arrives. The flare is the flash. The CME is the actual weather system, and it's the one grid operators and satellite companies are really trying to forecast. Now, to understand why that blind spot actually matters, you have to go back much further than 2026. You have to go back to the one time this system was tested at full strength, in a world that had almost nothing running on electricity yet. September 1859. A British astronomer named Richard Carrington was sketching sunspots through his telescope, as he did most clear mornings, when he watched a brilliant flash of white light erupt from one of them. He'd just witnessed, and sketched by hand, the first solar flare ever observed by a human being. About 17 hours later, remarkably fast for a CME, most take a day or more, the storm hit Earth. Telegraph systems across Europe and North America, the most advanced electrical technology humanity had at the time, went haywire. Operators reported sparks jumping from their equipment. Some got actual electric shocks off their telegraph keys. Paper on the machines caught fire in a handful of documented cases, and in some stations, operators discovered something stranger still. They could disconnect their own batteries entirely and keep sending messages, using nothing but the electrical current the storm itself was inducing in the wires. The aurora that followed was seen as far south as the Caribbean, and reportedly bright enough in places that people could read a newspaper by its light at midnight. Later analysis of ice core samples showed the 1859 storm was roughly twice as intense as any other geomagnetic event recorded in the previous 500 years. Nobody died. Telegraph wires were the only electrical infrastructure on the planet, and even that limited network went haywire for days. Here's the honest, uncomfortable math. That same magnetic punch, delivered to the world we actually live in now, hits a planet running on power grids, satellite constellations, GPS timing signals, and financial systems that didn't exist in 1859 and weren't built with this in mind. We don't have to imagine what a smaller scale version of that looks like on a modern grid, because it already happened in 1989. On March 13, 1989, a geomagnetic storm, smaller than Carrington but strong, induced electrical currents in the power grid of Quebec, Canada. At about 2:44 in the morning, those currents overloaded a transformer at the Hydro-Quebec Network's James Bay system, and in about 90 seconds, 21 gigawatts of supply went offline. The entire provincial grid collapsed. 6 million people lost power, most of them still asleep, waking up hours later to cold homes in the middle of a Quebec march. Picture the actual morning that followed, because this is what the grid went down looks like in practice. The Montreal Metro stayed shut through the entire morning rush hour. Dorval Airport closed. Traffic lights across Montreal and Quebec City simply died, all at once, at intersections that normally handle the start of a workday. The Montreal Stock Exchange had to open late. Schools closed by mid-morning specifically because their boiler systems needed electricity to run the circulation pumps, and without that, there was no way to safely heat the buildings. Hydro-Quebec's own operators spent the night bringing dams back online one at a time, carefully, because reconnecting too fast risked tripping the same protection systems all over again. About 83% of the load was back within 9 hours. Some industrial customers, aluminum smelters and pulp mills whose equipment draws enormous steady power, waited considerably longer than that. Here's the detail that should actually worry you more than the blackout itself. One of the transformers damaged that night, at a nuclear plant in New Jersey affected by the same storm, had to be replaced. Large power transformers like that aren't off-the-shelf parts. They're custom-built, often overseas, and if a utility has to order one new rather than pull from existing stock, the lead time is a minimum of about 5 months, and that's the optimistic case, assuming no supply chain backlog. The U.S. grid, today, keeps only a limited strategic reserve of spares for these things, because they're enormous, expensive, and every utility assumes someone else will have one when they need it. This isn't a hypothetical risk that only lives in disaster movies. It's been formally studied by people whose job is putting real numbers on it. The National Research Council, in a 2008 assessment, estimated that a Carrington-scale storm hitting the modern U.S. grid could cause $1 to $2 trillion in damage in the first year alone, with a full recovery timeline of 4 to 10 years. A separate 2013 analysis from Lloyd's of London and atmospheric researchers put the range even wider, up to $2.6 trillion for the U.S. specifically. Other published estimates for the number of Americans at risk of an extended outage from a storm at that scale range from 20 to 40 million people, with outage durations that could stretch anywhere from about 2 weeks to well over a year, depending entirely on how many replacement transformers happen to be sitting in a warehouse somewhere when it happens. I want to be straight with you here, because it would be easy to take those numbers and spiral into, the grid is one flare away from collapse, and that's not honest either. Modern grid operators know about this risk. There are voltage regulation procedures, monitoring protocols, and specific operating changes utilities can make within that 15 to 30-minute warning window to reduce the danger to any single transformer. The 1989 event happened before most of those protocols existed. We are meaningfully better prepared than we were then. But meaningfully better prepared is not the same as solved, and this is exactly where the real story of 2026 lives. Not in the sun, but in what we've built underneath it since 1989. Solar cycle 25, the current 11-year cycle the sun is in, actually peaked back in October 2024 with a smooth sunspot count that ended up running well above what forecasters had originally predicted for this cycle. By the end of 2025, it was tracking roughly 30% higher than the previous cycle over the same comparison period. As of this year, solar physicists monitoring it describe it as being in a slightly declining phase. The sun, on the whole, is calming down, not ramping up, even though it turned out to be a noisier cycle than models expected going in. If you're looking for a reason to be more worried about space weather specifically because the sun itself is getting angrier, the actual data doesn't support that. What's changed instead is what's sitting underneath that same sky. In 1989, GPS as a public utility barely existed. Today, GPS timing signals, not just the maps on your phone, but the exact, synchronized timestamp GPS satellites broadcast are quietly load-bearing for things most people never think about. Banks use GPS timestamps to sequence financial transactions down to the millisecond, so that trades and transfers happen in the correct order across systems that are physically located thousands of miles apart. Modern agriculture runs enormous auto-steering tractors and combines off GPS positioning during planting and harvest season, often accurate to a couple of centimeters, and a farmer running that equipment during a serious ionospheric disturbance can lose that precision entirely mid-pass, right in the middle of a planting window that might only last a few good weather days each year. Power grids themselves use GPS timing to keep different sections of the grid synchronized with each other, so that alternating current arriving from different power plants lines up correctly. None of that existed in any meaningful way in 1989. All of it is vulnerable to the same kind of ionospheric disturbance a strong geomagnetic storm creates, because that disturbance can degrade or scramble the GPS signal itself on its way down through the atmosphere. And then there's what's actually in orbit, and here there's already a real example of exactly the fragility I'm talking about, not a hypothetical one. On February 3, 2022, SpaceX launched 49 brand new Starlink satellites into a low staging orbit, the standard altitude where each one runs diagnostics before climbing higher. A geomagnetic storm hit the next day. Not a big one, a G1, the weakest category on NOAA's 5-step scale, the kind of storm that happens hundreds of times in an average solar cycle and normally wouldn't even make the news. That mild storm warmed and puffed up the upper atmosphere just enough to roughly double the atmospheric drag those satellites were experiencing at that altitude. SpaceX tried to fly them edge-on, like a sheet of paper turned into the wind, to cut down the drag. It wasn't enough. 38 of the 49 satellites lost too much altitude, re-entered the atmosphere, and burned up within days. Millions of dollars of hardware, destroyed by a storm so minor that space weather forecasters hadn't flagged it as a concern in the pre-launch briefing at all. Sit with that for a second, because it's the clearest single example of the actual argument I'm making in this video. That wasn't a rare, extreme Carrington scale event. It was one of the most common, unremarkable categories of storm there is. And it still took out most of a satellite batch, purely because we now have so much more sitting in orbit, running so much closer to the edge of what the upper atmosphere can do to it on an ordinary day. In 1989, there was no comparable hardware up there for a storm that size to even threaten. So here's the actual contrast worth sitting with, and it's the one I promised you at the start. The sun is past its peak and heading toward a quieter stretch of its cycle. That part of the danger is easing. But the number of systems on the ground that depend on a calm, predictable magnetic environment, GPS-timed banking, GPS-guided agriculture, satellite-dependent communication, an aging transformer fleet with a thin spare parts safety net, all of that is growing, and growing fast, regardless of what the sun happens to be doing this decade. The threat that's easing is the one making headlines. The threat that's quietly building is the one nobody's tracking on a graph. Now, you'll probably run into a version of this story online that goes somewhere much darker. Claims that Earth's magnetic field is secretly collapsing, that a pole shift is imminent, that officials know a civilization-ending storm is coming and are hiding it, or that the current solar cycle proves some hidden agenda is accelerating the sun's activity on purpose. Let's deal with that directly, because it's worth being precise about where real science and internet doom-scrolling actually diverge. Earth's magnetic field does weaken and shift gradually over centuries, and geomagnetic pole reversals are a real, well-documented part of the planet's deep history, but they unfold over thousands of years, and there is no credible measurement showing one is imminent or accelerating on any timescale that matters to anyone watching this video. Every study cited in this video, from the National Research Council's cost estimate to Lloyd's risk models to the machine gun sun sequence itself, is publicly available, peer-reviewed, or published by an official space weather agency. This isn't buried information, it's just not the kind of information that trends. The scientists actually publishing on Carrington-level storm risk aren't estimating it as a near certainty either. Published odds for a storm of that scale happening in any given century range from roughly 1% up to about 25%, depending on the model and the researcher, with historical auroral records suggesting a reasonable average return period for the most extreme storms somewhere between 100 and 250 years. That's a real worth taking seriously range. It is not a hidden countdown, and it is not evidence of a cover-up. It's just genuine scientific uncertainty about a genuinely rare event. So where does that leave the actual, honest answer to why is this only the beginning? Not because the sun is getting scarier. It isn't this decade. It's because the 15 to 30-minute warning window isn't shrinking anywhere near as fast as our dependence on GPS timing, satellite constellations, and an aging transformer grid is growing. Every year that gap widens a little more, quietly, without a single headline-worthy event to mark it, the same way a G1 storm, the most routine, unremarkable category there is, was already enough to burn up 40 satellites in 2022. Go back to where we started. The machine gun sun sequence in June and July made headlines because it was dramatic to watch, and because a scientist gave it a name people would remember. But the actual lesson from that week wasn't about the flares themselves. It was that our best forecast, built on our best available instrument, still missed by 2 full levels. And that gap is the size of the problem we're actually living with. Not just this year, but for as long as we keep building more into a system that only gives us half an hour of real warning. If you want one sentence to take away from all of this, the sun is calming down, we are not. And that gap is the actual story. As for what's actually worth watching right now, as opposed to worth panicking about, NOAA's own 27-day outlook flags July 22nd as the next date with any real elevated potential, and even that is only expected to reach a KP5, a minor G1 level disturbance, enough to maybe nudge the aurora a little further south for anyone in the northern US, nothing close to what hit Quebec in 1989 or what the machine gun sun sequence produced in July. That's the honest scale of things right now. Quiet, with one small, unremarkable bump on the calendar. We'll keep tracking this. Every X-class flare, every forecast miss, every update out of NOAA's Space Weather Prediction Center. If you want to stay on top of it, subscribe so you don't miss the next one. Tell me in the comments if you've ever seen the aurora somewhere unexpected. And if this helped you understand something you'd heard about but never quite had explained, send it to someone who'd find it useful too. Stay curious. I'll see you in the next one.